Okay, welcome. So in this video lecture, I'm going to be talking about how to use the FFT in MATLAB. This video is part of the amath481 course at University of Washington in autumn of 2016. And it's really a follow-up to the last video that I did on fast Poisson solvers. So if you wanted to implement the fast Poisson solver that I described in the last video, you really need to understand some key aspects of what the FFT function in MATLAB gives you. So we're going to talk about that here. Okay, so recall from last time, we want to use the FFT to compute these coefficients a sub k of the Fourier series expansion of our function f. And so the ak are given as the integral of f against e to the minus I pi k x over L. Okay? And the k in this situation is really kind of thought of as a frequency. So for the kth frequency, you integrate against e to the minus I pi k. Okay. Last time we noted that you can use the trapezoidal rule to approximate that integral using the values of f on just an equispaced grid, okay, that divides up minus L to L. Okay, so we said that this integral is approximately this sum, 1 over n f of xi e to the minus I pi k x sub I over L, where the x sub I are your equispaced grid points. Okay. One thing that we'll notice right off the bat when you go to call the FFT in MATLAB is this is not in exactly the right format. Okay. We'll get into that. Okay. So the FFT in MATLAB computes the discrete Fourier transform. Okay. So the discrete Fourier transform, DFT, is defined on vectors. And so you get an output vector G for a given input vector f. Okay, so we'll say f is given by f1 up to fn. And then the kth entry in G, right, G sub k, actually corresponds to frequency k minus 1. Okay? And so the kth entry in G is given by this sum from j equals 1 to n of fj e to the minus I k minus 1. Okay, so that's the frequency, times 2 pi j minus 1 over n. And so this part corresponds to a grid point on 0 to 2 pi. So you notice also then that the jth component of f really corresponds to the x sub j minus 1 point in our equispaced grid, right? If x0 is 0, then j equals 1 gives us that point on the grid. Okay. So our grid was centered. We used minus L to L. We should really then think of the basis functions as exponentials of this form, e to the I k pi x plus L over L. Okay, so functions of that form, right, have the same properties, of course, as the regular exponentials, but now they're shifted to align with what the discrete Fourier transform gives us. Okay? And the difference between the DFT and the FFT is that the DFT is just a definition. Right? The FFT is an algorithm for computing the DFT rapidly. Okay? I guess I should maybe say what I mean by that. So, right, in G we have n outputs for n different frequencies, okay? And each output is given as the sum over n terms. Okay? So naively, if we were to compute all of the G just using the formula, it would cost n squared multiplications and additions. But the FFT, right, the fast Fourier transform algorithm manages to do that in order n log n flops. Okay? So that's a very useful thing. Okay. So as I said, we wanted to use shifted functions so that it is aligned with what the DFT will give us. So let's rewrite that integral instead. We're going to redefine our ak as the coefficient for e to the minus I pi k x plus L over L. So these are slightly different basis functions, right? And so now our function will also correspond to those new sets of functions, right? F is now being expanded in these new shifted functions. Okay? So again, it's approximated by this sum, and now this sum is equal to the DFT applied to our vector f. And actually, in MATLAB, they're missing the 1 over n, but really other than that, it's equal to the dft up to a constant. Okay? And f then is defined by f sub j equals f of xj minus 1. Okay. Okay. But the FFT, as it's defined, would give us a0 up to an minus 1. And before in the notes, we said that we wanted centered frequencies, right? We wanted the coefficients for the frequencies corresponding to minus n over 2 plus 1 up to n over 2. Okay? So we actually want these coefficients, a sub minus n over 2 plus 1 up to a sub n over 2. Fortunately, though, this sum, right, the sum of the discrete Fourier transform that you get with n over 2 plus L actually is equal to this sum, where n over 2 is changed to minus n over 2. Okay? And this phenomenon is called aliasing, and it's an important thing to keep in mind when we're performing the FFT in MATLAB. And really what it's crucial for is kind of interpreting what the results mean. Okay, so we'll run a code later to show kind of in more detail what aliasing is. But for now, just bear in mind that while the FFT will say it's giving us the coefficients from a0 up to an minus 1, those values are actually equal to, in some scrambled way, the coefficients for a sub n minus 2 plus 1 up to an over 2. Right, so I'm just kind of restating the things here. On this particular grid, these functions appear to be the same, right? This is the aliasing phenomenon, because they take the same values just at that finite set of grid points. However, they are not the same functions, right? If you think about it, these n over 2 plus L functions have a higher frequency than these minus n over 2 plus L, because in that case, right, the plus L is decreasing the absolute value of that frequency. Okay? So we interpret the output of the FFT as giving us a0, a1, up to an over 2. And because of this equivalence, then the tail end we interpret as a sub minus n over 2 plus 1, a sub minus n over 2 plus 2, up to a sub minus 1. Okay? And it's important to keep this interpretation in mind when we go ahead and use the FFT to compute derivatives. Okay. Great. And then maybe to try to visualize things a little bit better, the output of the FFT, we said, we'll interpret it as giving us these coefficients, right? And these particular coefficients correspond to these basis functions, right? So the first n over 2 are exactly what you'd expect. a0 gives you e to the I0, right? So that's 1. A sub n over 2 gives you e to the in over 2 pi times x plus L over L. Okay, so that's the familiar basis functions. Okay. Then the tail end, right, we've got these equivalent coefficients, right? And so they are just going to correspond to the basis functions e to the minus I n over 2 minus 1. I've kind of pulled out the minus sign there, times pi x plus L over L, all the way up to the coefficient a minus 1 corresponds to e to the minus I pi x plus L over L. Okay, so those are, we think of these as now corresponding to different basis functions than if they were a0 up to an. Okay. And what does this mean for taking derivatives? So, right, we can still use the fact that the formula is easy to derive for the derivative of an exponential, but we just have to keep in mind what index we're at. So d by dx of these basis functions is going to give us, well, 1 gives us 0. Okay. E to the I n over 2 pi x plus L over L gives us I n over 2 times pi over L times the exponential. Okay. E to the minus I n over 2 minus 1 pi x plus L over L gives us what you'd expect, right? I times minus n over 2 plus 1 pi over L times the same exponential. So we still end up right with the same functions on either side, but we have these new coefficients, right? And then finally, right, e to the minus I pi x plus L over L corresponds to minus I pi over L times the same exponential. Okay, so while the same principles apply, really it's just we have this new order for obtaining the coefficients of the derivatives of our function. Okay, so now we're going to look at those concepts in MATLAB. Okay, so the first thing that we're going to look at is the aliasing phenomenon. I've got a script here that'll run through, and it will plot the functions e to the I n over 2 plus 1x and e to the I minus n over 2 plus 1x on that grid of sample points, right? So for a given n, we have n sample points, okay? And then I'm going to compare that to what the true function actually looks like for each. So as we pointed out, when you're looking at the aliasing phenomenon, these take the same values on that coarse grid, right, on that grid of n points, but they're not the same function. So if we look on a finer grid, we'll actually see the difference between the two. Okay. So here I'm going to set up an equispace grid on 0 to 2 pi with n points. And so here we're choosing n as a power of 2, which is something you always want to do when you're using the FFT and your problem doesn't restrict you to do something else. So we're setting n equals 8 here, and we're going to set up our grid of equispaced points, x, from 0 to 2 pi, and then we're also going to set up a fine grid of points with 1,000 points so we can actually get an idea of what these functions truly look like, because as we said, they're indistinguishable on the coarse grid. Okay? And then, as always with these periodic problems, we're going to cut off that last endpoint because it's really, in the periodic situation, the same as the first endpoint. Okay. And all that this script does is it runs through for the tail end, right? So it does the last n over 2 minus 1 functions, and it plots the real and imaginary parts of e to the I n over 2 plus I. And then, so that's on the top two lines. And then it compares those to the plots of e to the I minus n over 2 plus I, the real and imaginary parts of each. Those will be on the bottom part of our grid of plots. And also on each, we're plotting the function on the fine grid so that we can see really what it truly looks like. And then on the coarse grid, right, we'll see what the routine thinks it is because it's only evaluated on those coarse grid points. So we'll just run that code. Okay, and it'll generate a bunch of plots. Okay, so here, right, we have for the situation where we're looking at n over 2 plus 3 and minus n over 2 plus 3. So in our situation, right, n is 8. So we're looking at the mode for 7 and minus 1. And so if we look at the green, right, in the green we've plotted what the function looks like just at the coarse grid. And you'll notice that the green function for both the plus n over 2 plus 3 and the minus n over 2 plus 3 looks identical. So we've got the real part over here and the imaginary part over here. Okay. But if you look on the fine grid to see what these functions actually look like, of course, e to the I 7x is much more oscillatory than e to the minus ix. So that's how these two different functions can register as the same function because we're using this specific coarse grid. Okay. And we have the same situation for this is the fifth and minus third e to the I 5x and e to the minus 3ix. Okay, we see right there the green show that they're the same on the coarse grid, but the blue really shows that this is much more oscillatory than this slower oscillating function. All right, to just really drive it home again, we're looking at the case for e to the I6x, which aliases to e to the minus I4x. Sorry, e to the minus I2x. Okay, and so right, the values on the coarse grid look the same. That's the green in each, and the blue, right? The blue gives us these fine grids that show us what the functions truly look like. Good. So now that we're aware of the aliasing phenomenon, we can do a much better job of interpreting what the Fourier series means, right? What the FFT returns us, and it allows us to kind of more competently use the FFT to, say, take derivatives. So we're going to show how you can do that accurately with another script. Okay, so this script is pretty simple. We're going to set up a domain of width 2 from -1 to 1, so that's what L specifies. And we're going to set up quite a few points on it. We're going to do n again as a power of 2 because the FFT is more efficient for powers of 2. We're going to use n equals 2 to the 10th, which is about 1,000 points. And we're just going to use the FFT to compute the first, second, and third derivatives of a function. And we're going to compare that to a finite difference approximation just to make sure we're getting the right values. This is a good thing to do to make sure you're getting the scaling right and things like that, even though the derivatives that we obtain using the FFT are very likely to be much more accurate than the ones that we got using the finite difference approximation. So let's just kind of walk through the code. And really, this is where the aliasing comes in. It's right off the bat. So, right, because of aliasing, the FFT says it's giving us k equals 0 up to n minus 1, right, for the frequency. But we shift that last chunk of the frequency kind of over to these negative numbers. And so that's what we've expressed down here. So the scaled versions of the frequencies are given by the 0 up to n over 2. And then we say, all right, n over 2 plus 1 maps to minus n over 2 plus 1, and so on all the way up to minus 1. Okay? And I've called this case scale because I'm scaling by the relative length of our interval, right? Our interval is length 2L, but typically you would define it for intervals of length pi, so that's where this pi over L comes into play. Yeah. And then it's really simple. Using those formulas that we have, right, for the term-by-term differentiation of our series to figure out what factor you need to multiply by to obtain the first derivative and second derivative and third derivative. And it's actually really easy. Once you've set up this formula for the first derivative, which just gives you 1i times the scaled version of the frequency, then the second derivative is that times itself, and the third derivative is the derivative times the second derivative. Constants. So, right, that's very easy to set up once you have the correct scaling for k. And then finally, we've just set up a periodic function of interest. And like in the other video, we've got a part that is quite clearly periodic, the sine of 3 pi x over L term. And then I've also got this very narrow Gaussian term thrown in there, the e to the minus 30 times x squared. And as we said before, that is seen as being effectively periodic because it completely dies out and its derivatives die out by either endpoint so that those all match up. Right? We set up our space of equispaced points. We grab only the up to the second to last point because of periodicity. And then we evaluate our function at all of those points. So let's run the beginning part of this code, and we'll look at what our function is. Okay, so this is our function f. right, it's got that kind of oscillatory mode underneath, and then it's bumped up around 0 because of that Gaussian. Okay. All right, so after that, we can look at we can get the coefficients of f just by calling the FFT. Okay? And here we're going to look at the coefficients that we've obtained and just to see that whether or not our function is well resolved. And a test of that is if your coefficients decay, right, as you go to minus n over 2 and n over 2, then you know that you've probably resolved your function. And to move the coefficients into the right order for plotting that way, right, for plotting from minus n over 2 to n over 2, you can call this FFT shift function, which really just takes that end part and it flips it over. Okay, so we'll run that part of the code. And here, so we see a plot of the magnitude of our Fourier coefficients. And right, as these go out to the tails, this is towards minus n over 2, and this is towards n over 2. Okay? And we see that, right, of course, it's peaked around the center, and it decays rather quickly. Okay? So we're down around, floating around machine precision here. And that tells us that we're pretty well resolved. Okay. And then to compute the coefficients that correspond to the derivatives is extremely easy. So we go through and point-wise multiply the coefficients for f by that factor that we determined above for the derivative. So the coefficients corresponding to the first derivative are given by the constants that we determined for the first derivative times the coefficients of f, okay, and so on. So we've got the first derivative, second derivative, and third derivative. And then to actually get the values of f prime, f prime prime, and f triple prime, we have to call the inverse FFT. Okay? And so we haven't really talked about the inverse FFT in the notes, but it just undoes the FFT operation. And once you're shifting correctly, once you're interpreting the coefficients, and once you're interpreting, the frequencies correctly, you really don't have to worry so much about what the FFT and inverse FFT exactly mean, because they will undo each other. So you just have to make sure you're doing the right operation when you're in frequency space, right? So we'd say that because we're computing the coefficients based on the coefficients of f, this is an operation in frequency space. And the IFFT is just what allows us to return from frequency space back to real space, right, back to the grid. So to evaluate the series corresponding to these coefficients, we simply call the IFFT of each. So we've got our first derivative, second derivative, and third derivative computed that way. Okay. And then, then we'll test them. So let's just make sure that we run that whole part of the code. All right, and now it comes time to test whether or not we were getting the right values. And so we're just going to do it visually here, but you can do, of course, more sophisticated things. And what we're going to do is we're going to set up the matrix of finite differences. So what this routine does is it sets up the centered finite differences on a periodic grid. It's a rather easy routine to create. So we've got now a matrix that when applied to a vector should differentiate it. Of course, the center differences really aren't as accurate as what we're doing with the Fourier series, but it will tell us if we're right in the right neighborhood or not. And then we're going to plot the derivatives that we computed using Fourier series, and then we're just going to compute the derivatives that you would get using finite differences. And so we're going to plot each of these for the first, second, and third derivative. Okay, and this is the result. right? We've got the first derivative here, and as you can see, let me get the colors right. Okay, so in green, we plotted what we computed using the Fourier series, and in a dashed blue line on top, we're plotting what you get using finite differences. Okay, right? So we see that the green, right, the Fourier series-based derivative matches up extremely well with the blue, the finite difference version, and it works for all of the first, second, and third derivatives. And that's it. That's how you can manipulate Fourier series to give yourself derivatives. And also, right, you can undo derivatives. You have to be a little bit careful around the modes corresponding to frequency 0, but yeah, really, this is all that you need to know to solve differential equations, at least in the periodic setting. Okay. I will post the slides corresponding to this talk, as well as all of the code online. And thanks, I'll see you next time.